So I won't waste too much time talking about the basics of testing in Go, but I'll just quickly recap how it works for those of you who might not know. So Go has a testing framework that's built in to the language and toolchain, well, not so much the language, but the toolchain. And it's provided by two pieces. There's a package called testing in the standard library, which provides some testing hooks and helpers. And then there is the Go tool, which implements a subcommand called test, which runs those tests. And so this is a file which would be called, say, strings_test.go. And it's a cut down version of a test from the string package in the standard library. That should actually be strings test. Oops. And in this file, we have a function called test index. That's capital T test, capital I index, and it takes a testing T argument, which is a little help test handler helper. And then the test actually just calls the function strings.index, passing in the string and the substring, and then you get the expected result in the got variable, compare it with the value that you wanted, and then use the T argument to report an error if it doesn't exist. So you just write tests in Go as normal Go code, as Go functions. If you want to write a table-driven test, you can just use a Go struct literal. You just create a variable which is a slice of test cases. You can just put a little struct definition in line inside your test, which has the inputs and the expected output. And then you just enumerate your test cases in this slice literal here. Then to actually run the tests, you iterate over that slice, doing the same thing as before. And so again, there's no sort of special macros or anything. It's just plain Go code. And so the testing T argument, which I mentioned, is used for reporting errors, but it can also be used if you call t.fatal to bail out of a test midway through if the test has kind of failed unrecoverably. You can use the log function to print log messages if you run go test with the -v flag, which can be useful for debugging your tests. You can also do a couple of other things which you might not be familiar with, which is if you call t.parallel near the top of your test function, it marks that test as being safe for parallel execution with other tests of that same nature. And so it means if you have several tests that can all be run in parallel, you just call t.parallel early on in the test, and the testing framework will parallelize the execution of those tests across however many cores you have in your system, which can be great if you have large CPU-intensive test cases. There's also this cute function called skip. If you have a test case that doesn't work on a particular platform or under certain conditions, you can call t.skip. And what that does is it bails from the test without failing the test, but it logs a message to the console saying, skipped test foo because, and in this case, I'm saying it doesn't work on ARM. And so it's quite common if you have some library that's kind of Unixy, you might stub out your tests on Windows or some of those tests, something like that. As I mentioned, the Go tool is used for running tests. So you type go.test, go test on the command line, and that will run the test for the current package. Go test -v if you want to see what's actually running. If everything goes well, you'll just get a string pass. If things don't go well, you'll get the failure explained there. You can also, of course, use wildcards. If I want to test all of the code in my GitHub account, I would use that with the ... That's the kind of wildcard as far as the Go tool is concerned. Or if you wanted to run the test for the standard library for some reason, you can just use the std abbreviation. So that's the basic testing framework. There's also some other useful parts of it. For instance, there's a test coverage tool built into the tool set. And so if you run go test with the -cover flag, what that actually does is it rewrites your package source code and inserts test coverage annotations throughout the source code so that before and after each statement, it increments counters to say, I visited this piece of source code. Then it runs your tests with this modified version of your package. And when the tests have completed, it looks at all those counters and sees where in the code, which statements in the code have been executed during the tests and then it can tell you the test coverage, how much of your code is actually tested by your tests. And so in the strings package, it's 96.4% tested. And that's not a particularly useful figure on its own. I mean, it's good to know that, you know, most of the package is tested, but you can also generate a coverage profile by using the cover profile flag, and that will generate a file which dumps all of that counter information, including line numbers and so on. And then you can interpret that coverage profile using the cover tool. So if you type go tool cover, it gives you access to this command line tool that will, if you use the -func flag, you pass it the coverage profile, and it will enumerate all of the functions and the percentage of lines inside those functions that are covered by your tests. But even that's not really that useful. So we actually have, well, it is very useful, but it's not as useful as it could be. If you use -html, it will generate a HTML coverage visualization, and you can page through the different files inside of your package, and it will show you like which lines are covered in green and which ones aren't in red. And you can even, there's a mode you can put it in which will show you with a color gradient, you know, which lines are executed the most during your tests, which ones are executed only once. You know, that's kind of useful. Do you have a question? No? You're just waving your hand around? That's fine. So that's coverage, and coverage is actually pretty handy, and we'll see why in a moment. So who here knew everything that I just said? Yeah, at least an eighth of you. That's fine. But I'm going to talk about some stuff that maybe nobody in the room knows, or only a few, even fewer. But to talk about them, I want to use an example. And some of you have probably seen this example before. I've used it in other talks. It's a nice small web server. It's called OutYet, and it's a web server that reports whether a particular version of Go has been tagged or not. And so there is a version of this running at isgo1.1outyet.com. And as you can see, it's been a couple of years now. So of course, yes, it is. And if you click through on the link, it takes you to the Google Code webpage where we see my change that added the Go 1.1 version, and this is the tag. But so what this website does is it continuously polls this URL. If you can see that up there, it's code2go.com/blah blah blah /detail, and the query string is r equals Go 1.1. So it's asking Google Code to show the version of Go, sorry, the change in the Go tree that is tagged Go 1.1. And so if I go to Go 1.2, you see the one for 1.2 and 1.3 and so on. And 1.4 is not out yet. And so Google gives us the generic Google 404 error. It says that's all we know. It's not really all you know. It's all they're going to tell you, though. So what the web server does, the OutYet server, the thing that powers this website, is it continuously polls this URL like every 5 seconds or whatever. And while it's getting a 404, it knows that Go 1.4 hasn't been released. But then as soon as it gets a 200 OK, it knows, it's been released. I can tell the world. And so it changes what it reports. And so I actually have a version on my machine here. If I run OutYet with version equals 1.4 and allow it to listen on ports and visit localhost 8080, you'll see Go 1.4 is not out yet. All right, and we can just take a quick look at the main.go. It's all just using stuff from the standard library. We have some command line flags, the version to display. I'm just going to hard code localhost in there so I don't get that firewall warning again. The period to poll and the address to listen on and so on. We got the base of that Google Code URL that we were hitting. And then when in the main function, it just determines the change URL based on the provided version, just appends the version to that string. And then it registers a new... Someone close that door. And just tell him he's an idiot as well while closing the door. Thanks. What it does is it creates a new server, this new server function, and that returns an instance of the out yet server, and which you can see at the bottom of the slide, bottom of the page, and it registers that as the HTTP handler for the web root, and then it sets up a web server listening on that address, and will log.fatal if that listen and serve fails. So just the usual kind of pattern for setting up a web server. The actual server itself is pretty straightforward. It's just a struct type. It has a few fields, the version, the URL, and the polling period, how often to hit Google code. And then it has this piece of shared mutable state, which is this Boolean field, yes. And its default value is false, like the version hasn't been released. As soon as it has been released, it will be set to true. And so the user interface reads this piece of shared state to display to the user yes or no, right? In this constructor function, new server, we take a version and a URL and the period to poll, construct a server object. We call this poll method in a new Go routine, so it's running in the background, and then it returns the initialized server. The poll Go routine is really simple. It's just, first there's a for loop, which just checks whether the given URL is a tagged revision or not. And if not, it sleeps for the poll period and then does the same thing again. Once is tagged returns true, once the revision has been tagged, we take the mutex that's protecting our Boolean field, set it to true, and unlock. And then that poller exits, its job is done. As soon as the Go version has been released, it's got nothing more to do, so it just returns, shuts down. The isTagged function is really trivial. It just does a head request to that URL. If there's an error, it prints the error string. If the stat, and then it just returns whether the status code was 200 OK. All right. So that's the polling side of the program, and then concurrently we have this user interface, which is this serve HTTP method. This is an HTTP handler implementation. That's why we were able to pass the server type to the HTTP handle function. The serve HTTP method just takes the read lock of our mutex that's protecting the shared state, and then it sets up this data struct which has the URL, the version, and the value of yes, and we pull those straight out of the server type, and then we release the lock, pass that data straight into this template, which gets written to the network connection, to the user's HTTP connection. So they see this template here, which provides the user interface. So this is just using Go's HTML templating package. It just inserts the Go version in there. If yes, it prints the string yes wrapped in an anchor tag with the URL. Otherwise, it just prints no. All right, so that's the example program. And so it's pretty simple. And looking at it, it's if it seems to work, it probably works. But we don't know anything in this world, this crazy world, and so we need to actually write some tests for it. But testing this is kind of non-trivial because it's not just a standalone program. It's not just some functions that have inputs and outputs. It's actually something that exists in the world that communicates with servers elsewhere and has clients that connect from elsewhere. And so it's not this kind of like nice little isolated thing. We need to actually interact with it as a client and also as a remote server. And so to do that, I'm going to introduce these test HTTP clients and servers that are in the net HTTP test package. So that's at golang.org package net HTTP test. And so there's a bunch of stuff in here. The most important two things, well, the only two things, I guess, the server type and the response recorder type. And so I'll talk about both of them now. So the test server is a bit like what it sounds like. Basically, it's a type that implements an HTTP server just using the net HTTP package. And you just pass it a handler in this new server function. And it will listen on a random port on localhost and then give you back a server type. And it will populate this URL field with the URL of that localhost server. So it'll be like something like http://localhost:3000/. And then in your tests, you can make requests to that server, and they will all be answered by the HTTP handler that you provided the server. And then when your test is finished, you just call this close method. Now, there's some other stuff here inside the struct, which is useful, but not really pertinent right now. So to give a really simple example of the test server in action, this is a function that it creates a test server using HTTP test new server, which it passes this handler function, which simply writes the string hello golang-syd as the HTTP response. So now we have this test server TS. We defer the closure of that server until the function exits. So that means that when the test exits, the server gets shut down, the port gets released, the test server disappears. And then we make a HTTP GET request to the test server's URL. And if that fails, we want to fatal out. And then we read the body and finally print the body to standard output. So if I run that, what happens? It sets up the server, makes the request to the server, gets the string from the server, and prints it to standard output. So let's apply that to this program. So the obvious place to start testing is this simple function is tagged. We want to know whether this function, when it hits a URL, does it return true when it gets a 200 OK, and does it return false otherwise? All right, so I'm in this directory. There's nothing in there. If I go to main, if I create a file main_test.go, this will still be inside my package main. And then I'm going to create a function test is tagged, because that's the function that I'm testing. And then the first thing I want to do is set up a test server. And this, I'm going to pass a handler function. In fact, because I hate typing this. And I'm going to delete it in a second anyway. I pass it this handler function, and all this handler function is going to do is just write a header with the given status. And so what's status? Status will start off as 404. Okay. I'll defer ts.close because I want to shut it down when the test exits, so I don't just leave it dangling around while my tests are running. And then I will make a is tagged call to the test server URL. And so if I get a true now, then that's an error, right? I'm expecting it to say false because the status that I've set up for my test server is 404. So if I get a true now, I want to write an error. And then I want to flip the status to 200 OK. And I'll take that and I'll do the same thing again, but this time flip the conditionals. Oops. Oh, and I hit save, and a tool called Go Imports, which maybe some of you might have heard of, sprung into action and rewrote my code to include all the relevant import statements, which is really handy. And if I throw a log in here and save that, it will add the log package, and then when I remove it, it will remove the log package, which is really, 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 really nice. Okay, so now that I've created this test, I want to run the test. So I'll open a new terminal and I'll run go test with a -v just to see what's going on. And incredibly, it compiled and ran and passed on the first try, which is great. And so that's my test for the isTag function. Pretty straightforward, I think. If I wanted to sort of beef this up a little bit, I could create like a table of statuses and expected true or false, and run through the gauntlet of potential HTTP responses. But I won't do that here. You can imagine that I did that. So the next step. So this is obviously a very, very small part of the program that we've tested. It's like a 3-4 line function inside 5-line function inside this bigger program. So now what I actually want to test is whether the server polls and observes the status and provides the right information to the end users. So I want to make sure that as long as my Google Code server is saying 404, it says no. And I want to know that after it flips to giving a 200 OK, it starts saying yes. So I want to test that. And this is more like an end-to-end kind of integration test. But to do that, I don't just need a fake Google Code server. I also need a like a fake user, right? And so to do that, I'm not actually going to create another test server that's running my server. I'm just going to invoke this serve HTTP method as if it's a client accessing it. And so I can provide a request, like the second argument. That's easy. I just do HTTP new request. But if I want to provide my own response writer, which in a typical scenario is the HTTP connection of the user that it's being written to. If I want to provide my own implementation of that, I can use the HTTP test response recorder. So as the name suggests, response recorder is actually a response writer implementation, but it doesn't actually send the response anywhere. All it does is record the response body into a bytes buffer and the header into this header map and the response code into this code. And it will also report whether the body was flushed and so on. So this is used inside the HTTP package for its own tests of its internals, but also in things like this. So to see this in action, here's another short demo. I have an HTTP handler function that just reports an error with the internal server error 500 response. And then I can create a request, which is just a get request to example.com/foo. And then I will set up an HTTP test recorder here and just invoke that handler function, passing in my recorder and the request. And then I can use the code field and the body field to extract what was actually written out by this handler up here. So if I run that, I should see 500 something failed. And if I change this to be something else, oops. I better pass in W. And run that one, you'll see we get a 200 response and my string. All right. So putting this into practice here, I'm going to go back over to my test file. And the first thing I note is I'll create a function called test. I'll do it above. Test integration, which takes testing T. And then the first thing I note is I need this thing again. But this is kind of gross. And so I'll just quickly rewrite it as something a bit nicer. I'm going to create a type called status handler, which is just an integer. And I'm going to put a serve HTTP method on it. So and what this serve HTTP method is going to do is simply write out a header, which is the status, which is the value of the status handler itself. So replacing my code here, I'm going to change status to be of type status handler. And then in here, I'll just pass a pointer to status as the handler itself. And now, if I execute this code again, check that it still works. But so now I just think this is kind of cute. I have an integer that implements an HTTP handler. I don't know. It's pretty much the only time you're ever going to want to do that. So embrace it while we're here and now, living our lives. All right. So I'm just going to copy that. And so I'm going to start off again with my fake Google Code test server reporting 404. And now I'm going to set up a new server, which is testing Go 1.x. And the URL is the test server URL. And the polling period, because I want my test to execute quickly, I'm going to make the polling period 1 millisecond. So it polls rather quickly. And so I'll just check my new server. Is that the order of arguments? Yep, version URL period. So that's set up my test server. And now, with the server running, I want to make a HTTP request. So I'll create a request, which is a GET request to the web root with no body. And then I'll create a response recorder. And then I will call the serve HTTP method, passing in the response recorder and the request. I'll just call this R because it's cuter. And now I want to actually check to see whether the test server has said yes or no. So I'm going to grab the body from the response body as a string. And then I'm going to say if it doesn't, I'll use the strings contains function. If the body doesn't contain the string yes, I mean no, then there's an error. I'm expecting no. And I'm going to say body equals %q. I want to print the whole quoted body string. And I wanted no. And so I'll put the body in there. And so the next test, I'm going to set up a new response recorder. And put in, and then call serve HTTP again. And then I'll do the test again, except this time I want to test for yes. There should be the string yes. And the one thing I forgot to do is in between, I need to change the status to 200 OK. Right, so above this line, my fake Google code is returning 404 and it should be not released. And below this line, my fake Google code is saying, yes, it is released. And so I should see a yes. Getting ahead of me. That's good. So if I run go test, keen-eyed among you will, well, should have spotted that. Nobody did. Very disappointed in all of you. Why doesn't that work? Oh, it's the writer, not the reader, not the request. Okay. It fails. I wanted a yes and I got a no. So why is that? Can anyone tell me? Can you really tell me? Right, exactly. So there's in between doing this test and setting this status and then doing the next test, there's been no time for my server to poll again. And so I can fix this really easily. I can just, after I set it, I'll just do a sleep for 20 milliseconds. And if I run it again, it passes, and that's awesome. So that's my integration test. And you know, it's pretty neat. I haven't had to do any dependency injection or anything. It just kind of works. But there are problems often in concurrent programs, and this is a concurrent program. And who's here has heard of a data race? So a race condition is when one thread in a system is reading from some memory while another thread is writing to that memory. And in most systems, the behavior of that is undefined. In Go, you just shouldn't do that. Unfortunately, we have this thing called the race detector to tell us when we are doing it. And the way it works is you run go test or go run or build or install and with the -race flag, and that will build your code with all of this instrumentation inside that instruments all of the memory accesses and will tell you at runtime if there has been racy behavior, so a read with a concurrent write to the same area of memory. And so what better piece of code to test it on than this piece of code? Now, I bet I need to install the race stuff. Nope, it's all good. You'll see the first thing that happens is I get a warning. There's a data race. Why? Well, we get a bunch of stacks. We can see that there was a read by this Go routine, number 13, on line 40. So what's line 40? What? Oh, line 40 is the part of my HTTP handler that's reading from this H variable. It's reading from the status. And let's look at the other line. The other line is on line 26 of main test. And that's here. That's where I'm updating that status variable. And so what's happening is this server is polling away one millisecond at a time. And during one of those polls, I'm updating the status, and there's a race because there is. And if that's not clear, I can explain more. But basically, I create this status handler. It is effectively this variable h inside this function. And so while I'm serving responses to the poller, I'm also updating the value that that response should be. And so there's a race. And so I need to do something about that. So when you're testing with concurrent code, like I just did, there's a temptation to use sleep because, you know, as human beings, we perceive the world, the universe as proceeding in an order from the beginning of time to the present into the future. But as we all know, time is an illusion. It's just another dimension like X, Y, and Z. We just have to get over that. Computers know that, though. And so to avoid the kind of flakiness that comes with relying on time during tests, we can use Go's concurrency primitives to actually take the variation, the flakiness out of the equation entirely. And so I'm going to do that here. And the way I'm going to do it is I will insert a couple of hooks that I'm going to override at runtime. And so the crux of this whole thing is this polling function. And basically, I want to stop relying on sleep. So I'm actually going to stub out the sleep. So I'm going to create a poll sleep variable, which is just a function pointer to time sleep. And so when I replace this with poll sleep, the code now behaves exactly as it did before. There's no functional change. But inside my test integration function, which exists inside the same package, I can actually override that variable with my own function, which takes a duration. But instead, inside my function, what I'm going to do is I'm going to create this channel, and then I'm going to do a couple of sends to this channel. So what I'm actually doing is turning that time.sleep function into a latch. So what I can do is wait until the sleep has begun by doing a receive from sleep. And then I can do another receive from sleep to unlatch the sleep function and allow execution to continue as if that duration has elapsed. So the first place that I want to, so if you can imagine, I create this new server, right? And then the new server launches this polling Go routine. And I want to make sure that I've at least hit this part of the loop. I want to make sure that I've hit my fake Google code server just once. And so I want to wait until we've entered the sleep function at this point. So what I'll do is do a receive from sleep here. So this means that once I've passed this line, the polling Go routine is sleeping effectively. And so now I'm safe to do my first request to the server's serve HTTP method here. and test to see whether I got the response that I wanted. And now, after I update the status, I know that my polling routine is still sleeping. I want it to stop sleeping. So I've changed the status to 200, and I'll do the second receive from sleep. And so for those of you who don't know, these are, does anyone not know what channel operations are in Go? Well, that's good at least. Basically, because these are synchronous, the sends and receives happen simultaneously. So you have two Go routines running, but they happen in synchronously. So I know that after I've passed this line, that this code here has exited the poll sleep function, and it's now back here at the isTagged function. And so it's going to see my updated value of the status. It's going to see my 200 OK response instead of my 404. All right. So now that I'm here, I've removed the sleeps. I still have 1 millisecond in the function call, but it doesn't actually matter. It's just ignored. And so if I run go test-race again, you see that I don't see a race condition, but I do see that my test is failing again. It's giving me no, as you can see here, when I'm expecting to get yes. So what's the deal? Anyone? Yeah? Yeah. Yeah, so when I do this, so I change the status, I receive from sleep, that allows this function to exit. It allows the function to exit. Meanwhile, in my test, I continue on and make the second request. But there's no actual guarantee. Whoa, that's bad. There's no guarantee that it actually ever calls isTagged again. Because in a concurrent system, the scheduler can schedule things whenever it likes until you have some kind of synchronization event. All bets are off as to when anything happens. And so I need some way to guarantee that I've waited until we've seen this and gotten down to here before making my second request. And so to do that, I'm going to put another hook in. There are lots of ways of fixing it, but this is the best way. It doesn't. Because when it goes around here, it never hits poll sleep again, because the next call to isTagged returns true, and so the for loop exits. So what I have to do is insert this little no-op function here, poll done. It's just this function that does nothing. And so again, in the production instance, it makes no difference. And then inside my test, again, I will override poll done, this time with my own function. And this is going to use another channel. And it's just going to send a single message to the done channel. And so I want to make sure that it's exited sleep and the polling Go routine is exited before making my second HTTP request. And so if I run go test-race again, you'll see that it passes. And so that's how I was able to eliminate the flakiness in my tests. And it's all just using the Go language itself to test the Go code, which I think is a tremendously powerful but very simple concept. There's one other thing that I've missed here. Does anyone know what that is? What if I'm testing the server in various different ways in different tests? What if I've got more than this integration test? Is there anything bad? I don't blame you for not figuring it out, but basically I've just overridden these poll sleep and poll done functions with my own stuff that's going to block until I receive from these channels. If I have another test that also tests this bit of the code, it's going to hit those bits and just deadlock and never be able to proceed. So like a good citizen, I should always create a deferred closure that after the function is done, it just puts poll sleep back the way it was, and poll done is again a no-op function. All right. So just obviously it makes no difference in this context. But whenever so this is effectively faking these things out, right? And it's a form of dependency injection. And so whenever you mess with code like this, you always have to put it back the way it was. It's just polite. Okay. Cool. And so there are other ways to find errors. One of those is with the superb vet tool, which finds things like bad printf strings, build tags, all kinds of stuff. There's actually so much in it now. And if you haven't run Go Vet on your code before, I suggest you try. If I run Go Vet here, you'll see that I've been remarkably well behaved. But if I go somewhere in this code here and change this error f to say an error call instead, which is another function that exists, it's not the right one. But when I run Go Test, I don't see anything wrong with that, right? Because I'm not there's no error, so I don't see the error formatted. I don't notice that it's wrong. But if I run Go Vet, it actually finds the error call. It knows it's something, but then it sees that I'm using printf directives in the, I'm using this %q. And so it's like, hey, you should probably be using printf. And similarly, if I was to use, say, a numeric to print that, it says it's a bad printf verb. If you try to print a string as an integer, it's obviously not going to work. And that's just the beginning of the ways in which vet can help you. And it's kind of scary to run vet on a code base that you've been working on for a while. You don't realize how bad your code actually is. So that's a really nice tool. The stuff that I just demonstrated, I had two files, the main.go file and main_test.go, and they're both part of the main package, so package main. But when the _test file is only compiled when you run Go Test. So when I just run Go install or Go build or whatever, it just builds main.go. But when I run Go Test, it builds both. And it builds them both each. If I look at the top of each of them, well, not that one. You see that main.go is in package main, and main test is in package main. And what that means is they can, as we saw with the poll done and the poll sleep overrides, I'm able to actually reach into the private implementation of the package from inside my tests. And so obviously that's really useful. You don't need to put your testing stubs in your public interfaces. You can keep it all nice and clean and self-contained. But sometimes you have situations where you can't actually run your tests in the same package as the code you're testing. Maybe you're using a package that depends on the package you're testing inside your tests. And so you create this dependency cycle if it were in the same package. A good example of this that's easy to think about is the testing package in the standard library uses the fumped package to format strings. But the fumped tests use the testing package. And so the fumped tests are actually all inside package fumped_test. And import both the fumped package itself and the testing package. And so in this way, we sort of sidestep the dependency cycle. And so if I go to the fumped package and look at, say, fumped_test.go, you see that it's in package fumped_test, and that it imports the fumped package, and then it just tests all of the names that are exported from the fumped package. But then you end up in the situation where, what if you want to test implementation details that are not part of the public interface, but you have this dependency cycle situation? And the way you do that is exactly what Fump does here. Is they have this file called export_test, and the Fump tests want to test the isSpace function. So there's a function called isSpace. It just tests whether a character is a space function, a space character or not. And so what we do is we have a file called export_test.go that's in package fumped, which simply creates a variable that exports that function isSpace. Right, so isSpace is declared in another file somewhere in this package. But what this means is export_test is only built when we're running Go Test. It's not actually built otherwise. And so it means in my bump test, when we're testing isSpace, you see it actually says that is_space is lower is_space define and export test.go. And so that's a really neat little trick there. All right. I just want to talk a little bit about mocks and fakes. Go eschews a lot of things, including mocks and fakes. Basically, the general approach is to instead write code that takes interfaces. So if you're writing a file format parser, don't write code that takes a concrete type os.file. Instead, you want to write a function that takes a reader, like just an interface type that specifies the methods you actually want from the file. And so in this case, if you're writing a parser, you're really only interested in reading bytes from the file. You're not going to write to the file while you're parsing it. It doesn't really make sense. And so if you write your code in this way, taking a reader, I can actually use any implementation of reader to feed data into the parser. Even if whenever it's used in production, it's always reading from a file, it's better to structure the code in this way so that your tests can actually just use, say, a string reader to take a test string and feed that into the parser. And so that's generally how we get around dependency injection frameworks and just like large mocking frameworks and all that kind of stuff, is just by writing code that uses small interfaces. And then we just have small fakes like the response writer, like the response recorder that we saw. Small fakes that allow us to inspect how they were used. And there are frameworks that generate those kind of fakes. One of them is called Go Mock, written by somebody who's in this room, who I won't name. And they're fine, but I find that on balance, the handwritten fakes tend to be easier to reason about and clearer to sort of see what's going on. That's my personal experience. But I'm not an enterprise Go programmer, so maybe people do need that. I don't know. That's my advice. All right, just have one final little topic in this sort of grab bag of topics, which is sometimes you need to test functionality that acts on a process level. And so let's say I have a library that has this function called crasher. It's not a very useful function, but basically it just prints a string to standard output and exits with an exit status of 1. And I want to make sure that this crasher function actually does what it's advertised to do. But if I just wrote a normal test in the usual style that called crasher, it would exit my process, but the running process is actually the test process. And so my tests would just crash as well. And so obviously that's undesirable. It's not really, doesn't really help. Sorry. If you don't use Flux, you actually should. It's amazing. So test crash. The way I'm going to get around this is when I write my test, this test crasher function is actually two things simultaneously. One, it is going to be the test itself, and two, it's going to be a subprocess that my test runs. And so if you ignore this if statement at first, the first thing I do is execute this test binary, the binary that's actually running the test, with the flag test run test crasher, and with the environment variable b_crasher set to 1. And then when I run that function, that command, it will re-execute my test binary, but this time this if statement will return true, and I can call crasher there and return. And so instead of, and so now I'm having a test binary that calls itself and it executes some code on behalf of the parent process. And then in my code here, I can actually test whether I got a success, like an exit status of 1 or 0. And if I didn't, I can write a fatal, I expected this and I got that. And so this is this is basically the smallest possible example of a subprocess test I could kind of formulate. But if you look at, say, the HTTP packages tests, it has tests that spawn multiple subprocesses with servers and clients that talk to each other over the actual network and stuff like that. And so it's actually really powerful to use Go's testing framework to build like larger scale integration tests that actually bring up pieces of your infrastructure and have them talk to each other and so on. You don't need to go out to some other kind of framework to do that kind of stuff. And so I think that's a really nice thing about the way Go's testing framework works.